Welcome everybody to the next video in our series on real analysis. I, as always, am Dr. Theorem, and today we will be talking about compact sets. Alright, so let's begin our discussion of compact sets. And to do that, we'll begin with a couple of definitions. So first, the definition of an open cover. So let's say that we're given a metric space XD, and that we've got a subset E that's going to be a subset of our space, and that we're given a collection G sub alpha of open subsets of X. Now, an open cover the collection G sub alpha is going to be an open cover if and only if we take the union over all of the elements in that collection that actually has E as a subset. So quite naturally, when we say open cover, it does cover, putting them all together does cover the set of interest. Now for our second definition is actually that of a compact set. So again, we're starting off with a metric space XD. So a set K in X is said to be compact if every open cover contains a finite subcover. And so for however complicated this particular open cover might look, we can always just reduce that down to a finite set of elements from that cover, and that's going to be the key thing there, that it's a finite set of elements that actually covers our set K. And so that's really what we mean by a compact set. So really, what's the idea behind this notion of compactness? So we've seen the definition, but now if we kind of think outside the realm of mathematics, whenever we think of compact, basically what comes to mind is something that can be made small and put in your pocket. Ironically, that's really not too far from kind of the idea of where things started with the notion of compactness, that we can think about a set really not being able to spread out very much. And kind of, as we'll see, that was a lot of the motivation and really the implications that we saw in the case of finite dimensional real space. So where exactly did the history of compactness actually come from? Well, going back to 1817, we have Bernard Bolzano, who was investigating sets that were closed and bounded. And something that he happened to notice was that each one of those sets that was closed and bounded did have a subset of points, did have a sequence of points that actually did converge to some number, so it had a limit point. That was then extended by Karl Weierstrass, who kind of rephrased that and reformulated things so that we could actually apply it to spaces of functions and not just kind of spaces of geometric points. And so we were able to then treat functions as points. What that led to was then a further generalization when you start talking about families of continuous functions and uniform convergence, and so you end up with these something called the Arzela-Ascoli theorem from Giulio Ascoli and Cesar Arzela. And so that kind of gave us a more of a generalization of the Bolzano-Weierstrass theorem. And not to be outdone, probably familiar with this, was this notion of compactness and kind of things not really being spread out. We have the work of Edward Heine and Emile Borel. And you probably are familiar with their Heine-Borel theorem, which says that at least in finite dimensional real space, that compactness is actually an equivalent condition to being closed and bounded. And so that's kind of our really the idea that its compactness is really not being spread out. And that worked very well for a little while. And so what the real problem was the idea of dimension. And so we've got the following theorem from Kreitz's Introductory Functional Analysis with Applications. And basically a theorem that states if we have a normed vector space X that has the property that the closed unit ball is compact, then X is finite dimensional. And so you can see kind of the equivalent statement of that is that if we've got an infinite dimensional space, then the closed unit ball could not be compact. And so basically when we've got an infinite dimension, we've got enough room to spread out and still not be compact. And so in the infinite dimensional case, we kind of lose this connection of between compactness being equivalent to being closed and bounded, because obviously the closed unit ball is bounded. It's just the set of points of distance 1 from the origin, so it's obviously bounded. We assume that it's closed, and so in the infinite dimensional case we lose compactness in that case. What we really mean by a norm is just nothing more than a function that's going to allow you to measure the quote-unquote length of vectors. And so to kind of put this in the context that we're dealing with, if you've got a norm, then we can simply define a metric by taking the distance between two vectors x and y to just be the norm of the difference between the two vectors. And so the references that we've kind of used in this video, we've got Kreitz's Introductory Functional Analysis with Application by Wiley, 1978, if you want to go look up more about the unit ball and compactness. The definitions of compactness came from Rudin's Principle of Mathematical Analysis. And finally, if you want to go back and read a little bit more on the history of compactness that we talked about at the beginning of the video, there I will point you to Wikipedia. So I hope you've enjoyed this kind of introduction to compactness, and stay tuned for following videos on the subject.